Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS in Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to limit our time to an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on eliminating risk from PFAS contamination via low-cost, in-situ remediation with colloidal activated carbon. With that, I'd like to introduce our presenter for today. We are pleased to have with us Scott Wilson, President and CEO of REGENESIS. Scott has extensive experience in the development and application of advanced technologies for groundwater and soil restoration. He is a widely published expert with over 30 years' experience designing, installing, and operating a broad range of remediation technologies. He has expertise in project management and has directed the successful completion of large industrial remediation programs under state and federal regulatory frameworks. At REGENESIS, on specific projects, he plays an active role in technical oversight and program management to ensure conformance with customer expectations. All right, that concludes our introduction. So now I will hand things over to Scott to get us started.
Well, thanks very much, Dean. I really appreciate it. And thanks to everybody for joining us here. What I'd really like to go over and impart today in this 1 hour time slot is an introduction to colloidal activated carbon and an introduction to environmental risk, and then a focus on the use of colloidal activated carbon to eliminate that environmental risk. This is actually a sort of an extended version of a talk that was given just last week at the National Groundwater Association workshop, which was an actual meeting of sort of top regulators and consultants to focus on solutions to the PFAS problem that we're seeing around the world. So I hope to get through this and leave a little bit of time for questions. And with that, we'll move right into it. I want to acknowledge Jeremy Bernstengel and Kristen Thorson, who were both instrumental in the development of colloidal activated carbon technology, and who actually did a lot of the experimentation and development of what we'll talk about today. So first off, what is colloidal activated carbon? Well, first of all, it's not your grandfather's activated carbon. It's actually what we take is we take granular activated carbon, which you're used to seeing in carbon canisters on pump and treat systems, and we actually mill it down to the 1 to 2 microns. And most colloidal or most granular activated carbon is 1,000 microns in size. There is some that's only half that, 500 microns. We take that and we mill it down to 1 to 2 micrometers. And that's 2 to 3 orders of magnitude smaller than granular activated carbon. It's actually milled down to the size of a red blood cell, and we then suspend it in water. And first of all, carbon itself has a huge surface area, but when you take granular activated carbon and mill it to the size of a red blood cell, what you've done is you've imparted a huge amount of wetted surface area to the outside. In other words, you have a lot more surface exposed directly to the contaminant in the aqueous medium. As a result, you get extremely fast sorption. So how do we do this? And if you just had activated carbon milled to the size of a red blood cell, it would re-agglomerate into bigger chunks. So what we've done is we've figured out additives that we can add that allow for the suspension of these particles without clumping. And really what we do is we wrap the particles in a polymer that has negative charges all over the polymer, and so the net charge of the particle is negative, and as a result, all these negatively charged particles are bouncing around in suspension, repelling each other. So it actually stays in suspension. It looks like fountain pen ink. If you're familiar with fountain pen ink, it looks just like black water. And the result is it just flows into the aquifer. You can actually just pour it down not monitoring wells, but you can pour it down wells. You can pour it into the subsurface and it will just go in by gravity, or you can, under low pressure, push it into the subsurface. You know, most of the subsurface has pore throats that are lower than 10 micrometers in size. In other words, if you're trying to inject or flow material through sand or silts, most of the pore throats between those particles, which are much smaller than the pores themselves, require that the particle be smaller than 5 microns to move through there. And that's why we chose to get down to 1 to 2 microns so that it'll actually flow in the aquifer matrix flux zones. Once it goes down into the aquifer matrix flux zones, the negatively charged particles actually attach onto the surface wherever there's a positive charge. And realistically, we don't have time to go into it now, but what we're actually referring to is the zeta potential of the subsurface. The zeta potential of the aquifer matrix itself, where there's a negatively charged, or where there's a net positive charge rather, the negative charges will adhere. And once these particles adhere, that basically coating the subsurface, they don't move. They attach, and over time the polymer will degrade, but we do not see the carbon re-released. It actually becomes part of the aquifer matrix and stays in place. The other thing that's been very interesting is that when we load the colloidal activated carbon into the subsurface, as it coats these pores, you can do multiple coatings, and we've seen no impedance of groundwater flow. In controlled column studies with sand with a considerable amount of silts and clays, we can continue to flow plume stop through, wash it, put colloidal activated carbon, what we call plume stop, through, wash it, and see multiple times with no impedance of groundwater. As I've mentioned, when we put our additives into the carbon that's been milled down to the size of a red blood cell, we have what we call plume stop, and plume stop is really our brand of colloidal activated carbon with the additives. And after a project was successfully completed, there was a regulator who was reviewing the data, and he said something that really resonated. And he said, "You've converted the polluted aquifer into a purifying filter," and that's really what we do by putting colloidal activated carbon into the flux zones and coating those flux zones. We've turned that flux zone into a purifying filter, very much like a Brita filter. In fact, it's both, you know, the aquifer, once it's treated, serves both as a multimedia filter as well as a carbon filter. So it's a very, very unique and disruptive technology within groundwater cleanup. So here's an example. Colloidal activated carbon, our plume stop is on the left, and on the right is another product that's on the market, which is a powdered activated carbon product that people are fracking into the subsurface. You'll see that as you load the carbon on, what we're doing, by the way, is we're pouring water through here, and this is a 12-minute lapse. This is a 12-minute video here. What you saw was the colloidal activated carbon on the left actually loading on and flowing through the column just with head pressure of water. Again, and this sand has 11% silts and clays. It's a 1-inch column, and 12 minutes elapsed time, you saw it flowed right through. The powdered activated carbon on the right is too large to move through the pore throats. It just doesn't work. You have to fracture the subsurface to get it to go into the subsurface, and it's really not applicable. What I want to also mention here on the left, when you saw that plume stop move through, it was black as night. And then as you flowed pure water through, clean water, you saw that black turned to gray, and it has not changed. What happened is the plume stop moved through, leaving a paint or a coating of 1 to 2 microns on the sand itself, turning the column gray. That will not wash off. We've done columns, large 16-foot columns, where we've washed, I forget, something like 90 pore volumes through at high shear, and you cannot remove the carbon. It's now part of the aquifer matrix itself. So this is plume stop, and as you see, it's very easy to move through the subsurface. Unlike powdered activated carbon, that's a filter, by the way. It's just not moving through the filter. Sorry about that. But on the left, you see the colloidal activated carbon does in fact move right through the sand and silts with no problem at all. So here's what sand looks like. That sand column before the plume stop went through, you can see the clean facies there. These actual surfaces are very clean and shiny, if you will. Notice the scale at the bottom here. The scale is a 50 micron scale. Now we're going to move into 20 microns, and here this is after the plume stop moved through. You can see that you have all of this coating of carbon now on the sand. The sand has now been turned into a purifying filter. We're going to move in to a 10 micron scanning electron micrograph, and here you'll see these are all 1 to 2 micron particles coating the surface, and that's plume stop in place. So smaller particles equal much faster sorption. I mentioned earlier that it's much faster sorption. Well, I just want to be clear here that intraparticle diffusion is the same. So regardless, if you have a large carbon particle, once the contaminant is moved inside of that carbon, it doesn't matter whether it's a small particle or a big particle, the kinetics are pretty much the same once it's inside the particle. However, the smaller particles provide more exterior surface and shorter distance to all the sorption sites. So by having more of the outer surface facing the challenge concentration of contaminant in solution, there's more opportunity for it to move into the particle. And because it's a smaller particle, all of the sorption sites within that particle can sorb contaminant in a much shorter period of time than waiting for the contaminant to move into the center of a large particle. This is actually some data generated by Zhao. The paper is actually Zhao, Ehrlich, Chen, and Higgins. This is out of researcher Chris Higgins' laboratory at Colorado School of Mines. It was actually published in ES&T. And what's important here is that they took a greater than 500 micrometer particle. That's the light pink line. And they took that and they milled it. And they milled it into 4 different other cohorts of size particle. And they took these different sized particles and they put them in separate beakers. And they then added the same challenge concentration of PFAS to them in solution. And over time, they measured what the concentration of PFAS was in the aqueous solution in contact with this carbon. And you'll see here on the bottom, the x-axis is time, and on the left is the concentration at the time of measurement over the initial concentration. It's the log. What you see is the large particle, which is the pink line, over time sorbed very little contaminant out of the aqueous solution. You still see a lot in solution over time. This is 30 days. It still has a lot of solution, a lot of contaminant in solution. The smaller particles, though, as they get continually smaller, they sorbed much more of the contaminant out of solution. What you see is the 53 micrometer particle down here in the red was a dramatically more efficient at sorbing the contaminant from the solution. And this is all, by the way, the same amount of carbon, just in different sized particles. So the amount of carbon in a smaller particle was much more efficient at sorbing contaminants out of the water than the larger particle, even though the same total amount of carbon was used in each case. In fact, if you look at the red line, this reached equilibrium, meaning that it was totally sorbed all the contaminant that could sorb out of solution within less than a day. You'll see the larger particle, which is equivalent to the smallest of granular activated carbon available on the market. I think it's about 500. You'll see that in 30 days, it sorbed very little. in order to get to equilibrium, the same point as the red line, it would take about 90 days. So the smaller the particle, much, much faster sorption. And just an illustration of why this is one more time. If you had a pound of carbon that was 500 micron particle size, let's say this particle on the left is one of the particles in that pound of carbon, and you subjected it to PFAS within a day, you see that little red band of PFAS would have been sorbed onto that carbon. Let's say it's 1 micrometer, maybe 2 micrometers into that 500 micrometer particle within a day. Well, if you had taken that same amount of carbon, ground it up into colloidal activated carbon with 1 to 2 micrometer size, within that 1 day period, if you had a distance moved and diffused of 1 to 2 microns, you would have accessed all of the sorption sites within the 1 to 2 micron particle size. So there's the power of size. Smaller the size, the faster you reach all the sorption sites. So it's much more efficient in terms of absorption to have a smaller particle than a granular activated type particle. So how do we apply plume stop or colloidal activated carbon to treat sites? How do we utilize this material? Well, if you have a project site and the red represents the flux zones, contaminant moving in the flux zones. By a flux zone, I mean a zone of higher permeability relative to the surrounding strata. So up here it would be a clay or silt zone, in the middle would be a clay or silt zone, but here are sandy silt zones that are actually taking most of the contaminant towards this monitoring well. What we do is just go into the subsurface, map the high flux zones, go into the subsurface with either a geoprobe or a well, and simply pour or under low pressure inject the black plume stop. And it goes and moves through these flux zones, coating the flux zones and prohibiting back diffusion. And here is an actual core, and to give you an idea of how this relates, here's an actual core from the subsurface clearly documenting that we turned the high flux zones black, and whereas most of the clay, granted it's not treated by the plume stop, but when the contaminant back diffuses out of that clay into the high flux zones, it will in fact be sorbed onto the carbon itself and prohibited from entering the monitoring well. We actually undertook a study at Colorado State University at Professor Tom Sales' laboratory. His former graduate student, Dr. Kevin Saller, who's now with CDM Smith, undertook a study for us. We actually paid for an extension of an ESTCP funded study where they went into dual porosity sand tanks where there was sand and silt interbedded, and they actually contaminated the strata within the sand tanks with TCE and then flushed it for a period of time to mimic a pump and treat system. And in the actual ESTCP study, they then put in lactate to see if bioremediation would stop the back diffusion, permanganate, ZVI, all sorts of different mediation injectable techniques. None of the techniques did anything more than prohibit the appearance of the back diffusion for a short period of time before rebound overtook the treatment, and it went back to where you'd expect the back diffusion to be coming into the flux zone. So it went back to the typical level of concentration. When we actually undertook the same study with the same soil, the same people, and the same sand tanks with plume stop, when the plume stop was flowed into those flux zones within the dual porosity sand tanks, it prohibited the back diffusion from exiting the tank. And it actually, we got biodegradation. In that case, it was chlorinated solvents. We got biodegradation. So the point here is that colloidal activated carbon, when applied to these flux zones, will actually treat the flux zone and prohibit the impact of back diffusion coming from the immobile porosity in the lower permeable zones. So this is the way we apply plume stop, treating the flux zones and turning these flux zones into purifying filters. In terms of performance of colloidal activated carbon, this is an example. Now this is with chlorinated solvents, but just to give you an example of a typical treatment, within 1 to 2 months, generally you don't see any contamination showing up, or very low contamination showing up within the flux zones. You just, in your monitoring wells, you just don't see contamination if you've appropriately applied colloidal activated carbon into the subsurface in the area of that well. It's just simply sorbed and taken out of the dissolved phase. And in the case of chlorinated solvents, it's biodegraded. So in terms of how many project sites have been applied, or where colloidal activated carbon has been applied, over 200 projects around the world have been successfully treated with plume stop in Europe as well as in the U.S., Puerto Rico. So with that, that's the intro to. That's actually the intro to colloidal activated carbon. Let's move now to a little bit about fluorinated compounds, and then we'll move into risk. So perfluorinated compounds, in this case we have PFOS and PFOA on your screen. This is the PFOA, of course, is the carboxylic acid, and the PFAS represents a sulfonic acid. And here the intersection of these lines are the carbons, and you'll see these are perfluorinated. These are the two largest groups of compounds, but they are by no means the only compounds, and we'll get to that in a little bit. But in terms of how plume stop and PFOA and PFAS interact, this goes to what are called isotherms. So what, in order to show how it performs, in other words, how colloidal activated carbon performs on PFOA and PFAS, it's the same as with any carbon. You generate what's known as an isotherm, and an isotherm is a series of measurements where you have a challenge concentration of contaminant, and you subject it to an increasing amount of carbon, and you wait for that to come to equilibrium at each point, and you measure what the concentration of the contaminant is in the aqueous phase, which is along here on the x-axis, versus what's sorbed to the carbon on the y-axis at equilibrium. And as you have more and more carbon, you'll see, as you have a relative amount, the higher amount of carbon to contaminant, which is down in this area, you have much more efficient removal of the contaminant from the aqueous phase. As you measure each one of these carbon contaminant loadings, you plot it, and you'll see that the plot is not a straight line. If it were, I think it's called a Langmuir isotherm. This is a Freundlich isotherm because it has a bend in it, okay? It has a curve to it. And why they're called isotherms is that each one of these measurements are taken at the same temperature. And so you generate this curve. And again, I just want to stress that you have a much higher efficiency at lower concentrations of challenge contaminant compared to carbon. So the more carbon you have relative to the contaminant concentration, the more efficiently it removes at equilibrium the contaminant from the aqueous solution. Okay? So what's important on this is what's known as the Freundlich constant. The Freundlich constant is a constant generated in the equation for the curve, and depending on how the isotherm is generated, whether it's higher, up, or lower down, you'll have a different Kf. So for PFOA, it turns out that the Kf is 52, okay, and for PFAS, the Kf is 135. And what this means is if you take a 5 part per million concentration of PFOA, you would need 224 milligrams per liter of plume stop to take it from 5 parts per million to 0.005 parts per million, which is not much plume stop required. And you need even less for PFAS. relatively speaking, you need a lot more for chlorinated solvents like PCE. So it's pretty efficient. Plume stop's pretty efficient for PFOA and PFAS. But in reality, this isn't very relevant because these concentrations of PFOA and PFAS are exceptionally high. If you move down to more reasonable challenge concentrations of PFOA and PFAS, you'll see such as 100 micrograms per liter, you only need 8.4 milligrams per liter of PFOA to take 100 down to 0.1 parts per billion. So, and even less, and for PFAS, you need 9.8. So it's very efficient. And again, the lower the starting concentration of your contaminant, the more effective plume stop is. And again, these are pretty high. I mean, we're talking 100 to 0.1 micrograms per liter here. So what is this? How does this relate to what we're really trying to do? The question. So what happens over time? Isn't your carbon going to fill up? Won't the barrier, if you have a barrier or an injected area where plume stop's been injected into the subsurface, a flux zone that's filled, for instance, with plume stop sorbed onto the aquifer matrix, won't it fill up over time and break through? The answer is, as PFAS do not degrade, the answer is yes, it will break through eventually. Remember, the chlorinated solvents and petroleum hydrocarbons, once they're sorbed under the plume stop, will degrade, and you won't see them show back up in the aqueous phase. But with PFAS, eventually, the plume stop will fill up. So the question is, how long will this take? So this is all about retardation factors. And a retardation factor is often used in contaminant transport. Whenever we talk about modeling fate and transport of contaminants in the subsurface, we talk about retardation factors. And retardation factors are calculated directly from the KF, that Freundlich constant. Again, it comes back to the Freundlich isotherm and how much sorption you will have onto the subsurface, either fraction of organic carbon, or in our case, how much plume stop you have there. And there's an algorithm that's used to convert Freundlich isotherms into retardation factors, it's in this case it's equation 16 out of MT3D, which is a very commonly used contaminant fate and transport model that converts the Freundlich constants into retardation factors. A retardation factor, and this is what's important, is defined as a retardation factor of 1 means that the contaminant was moving the same pace as groundwater through the subsurface. A retardation factor of 10 means that the contaminant is moving at 1/10 the speed of groundwater. Okay, so with PFOA, if you have a mid-range dose of plume stop in the subsurface, say 2,000 parts per million, you have a retardation factor of 80 if you have a starting concentration of 1,000 micrograms per liter of PFOA. If you start with 100 micrograms, again, these are exceedingly high, you have a retardation factor of 570. Now we're getting into reality. If you have a 10 part per billion plume of PFOA, you have a retardation factor of 4,000. That means that the contaminant is only moving at 1/4000th that of water. For PFAS, it's even better. For PFAS at 10 micrograms per liter, you have a retardation factor of 10,000. What that means is the contaminant's only moving at 1/10,000th the speed of groundwater. So in order to move through a zone of plume stop, if it takes water a year to get across, it's going to take 10,000 years for the PFAS to get across. So let's translate this into an example site. Let's say we have a barrier of 16 feet. Now, what I mean by a barrier is if we've gone into the subsurface and either gravity fed or under low injection pressure flowed plume stop through an aquifer where it painted the aquifer flux zone with a 2-micron layer of plume stop, and that zone was 16 feet wide, so that a unit volume of water impacting that zone has to flow 16 feet before it gets on the other side. And we used a single application of plume stop at a mid-range dose of, let's say, 2,000 parts per million. And the seepage velocity is 160 feet per year. That means, I'm sorry, 160 feet a year. And let's say our challenge concentration is very high. It's 100 parts per billion of PFAS. Well, the groundwater transit time then would be 1/10 of a year, which is 36.5 days. In other words, a unit volume of water with the PFAS in it would take 36.5 days to get through that zone of plume stop in the subsurface. The PFOA transit time is 57 years. That plume stop is going to retard that PFOA for 57 years. And PFAS, it's 200 years. So that's the power of painting that aquifer flux zone with plume stop, converting it from a polluted aquifer into a purifying filter. So with regard to plume stop, we've tested it on all sorts of PFAS contaminants. And by the way, what you saw here was at 100 micrograms per liter, which is a very high concentration. And again, because our isotherm data is a Freundlich isotherm, we have much, much higher efficiency at lower concentrations. So lower starting concentrations perform at a much higher efficiency. So we'd expect to see much longer retardation with lower starting concentrations. But let's talk about other contaminants for just a minute. Plume stop doesn't work just on PFOA and PFAS. In fact, this is actual site water that was from a site in the southern hemisphere. It was sent up to us from down under for evaluation. And I just wanted to give you a look at what else we can treat. Here's the baseline. This is time 0 data. This gives you an idea of the concentration starting. Here's the control, which shows you what we had, what types of concentrations in the control with no plume stop. And then here we have plume stop. This is after, I believe, a 14-day contact. So we just wanted to make sure that we were fully at equilibrium. And you can see everything was below limits of quantitation, with the exception of perfluorobutanoic acid, which is below regulatory limits, but above method detection limits. And this is just a simple batch test, which really has little bearing on how it would actually perform in a, quote, barrier application, because this is showing the full brunt of the competitive sorption between the more hydrophobic contaminants and the more hydrophilic contaminants. When I say that, I mean hydrophobic is water hating, which means those that don't go into water very well, but they go into plume stop really well. That's the longer chain PFAS compounds. The shorter chain, more soluble, like the perfluorobutanoic acid, which is has a 4-carbon telomere on it. That compound wants to stay more in water than on the plume stop. And so here you see it showing up, and that's because there's more competitive contaminants in this mix. But if this was flowing into a zone treated with this whole mixture, you would see the more hydrophobic compounds stripped out early on in moving through the barrier, and that would leave sort of the virgin plume stop to sorb tightly the perfluorobutanoic acid series. So a little bit more about this. In red, you see what are known as precursors. And by the way, this analysis is actually the method 537 that was developed by the Unregulated Contaminant Monitoring Rule under the Office of Water at the US EPA. This is what most people use at different state levels to monitor PFAS. And in this case, you see 3 precursors in here as well. Precursors, if you're not familiar with them, they're actually compounds that were used in the manufacturing of the PFOA and PFAS, and are often co-contaminants. And they will actually oxidize in the subsurface. They can be biodegraded and oxidized. The end result of the oxidation, however, these are precursors here, are the carboxylic and sulfonic acids, which you see at the bottom. And so if you're familiar with the top assay, we're seeing many people now performing these total oxidizable precursor assays. And the reason for that is that they can then simply use the equivalent of method 537, and it will catch all of these precursors once they be converted to the sulfonic and carboxylic acids. The reason I bring this up is that the precursors are generally much more hydrophobic than their final endpoint when they're oxidized at the top assay. So we actually expect very high efficiency of sorption with plume stop on these precursors, probably much more than the oxidized end product. So we will be catching most all of these precursors very effectively with plume stop. So one other thing I want to mention is we actually, Dr. Jeremy Bernsingle and our team has spent the last 3 years developing a competitive sorption model, which actually shows the competitive sorption among challenge species against plume stop. And this is actually a center line down a plume, from the head of the plume to a toe of a plume, down a single transect, cut right through it from top to bottom. And it shows a, quote, barrier, a 16-foot zone of plume stop being emplaced, and what the resultant sorption is with the competitive species. Remember, anytime you sorb the carbon, whether it's in a GAC canister or whether it's plume stop sorbed on an aquifer matrix, you have this competitive sorption. It's actually a dynamic equilibrium where a contaminant sorbs, but it's only retarded, and it's going to come back off eventually. Whether it's PCBs or whether it's alcohols, they all are in a competitive sorption dynamic. So the question is, what is the interaction, and how long will it take before the more hydrophilic, least sorptive species leave the barrier zone? And we now have a very effective model that we can run on sites to show this anticipated competitive sorption before we move forward with an application in the subsurface. So that's available to you through us as well. So let's talk for a minute about environmental risk, and then we'll move into an actual case study. So environmental risk. Back in 1987, there was a gentleman named Dr. Frank Lawrence. He has since passed away, but Dr. Lawrence was a medical doctor who had a practice in Portland, Maine. He left his practice in Portland, Maine to start the world's first environmental risk assessment business. And Frank was very, very, very influential on the entire groundwater and soil treatment industry. He would go around the nation speaking to regulators and speaking to PRPs and talking about the actual impact of contaminants in the ground, in groundwater, and how that relates to cleanup goals. And he made the case that we need to have contaminant cleanup levels that are commensurate with the use of the land. And Dr. Lawrence was really the first one that came forward and expressed that environmental risk is equal to hazard times exposure. And you know, you can have a hazard out there, but if there's no potential for exposure, there's no environmental risk. And I remember Frank speaking to a room where you could hear a pin drop, and he asked the question of a group of regulators. He said, would you ever allow a 3-year-old child to stand within 10 feet of a man-eating tiger? And I remember it was silent. And Frank then said, it happens thousands of times a day in zoos throughout the world. It's just that there's a 6-inch thick sheet of safety glass between the child who's tapping on the glass and the man-eating tiger. The hazard exists there. It's a living, breathing, flesh-eating tiger. It's just that there's no potential for exposure. So the 3-year-old child jumps back in his stroller and his mom pushes them off to the seal exhibit. So what we've done is we've actually just limited the route of exposure to that hazard. And that example resonated with me. When we talk about elimination of risk today, well, risk-based corrective action, Rebecca, is now commonplace throughout the world. I mean, people realize if you put up the sheet glass, the tiger is not going to be attacking people. They realize that we can grant no further action letters if the plume is not expanding and if there's no receptor impacted. If that supply well of that surface water body isn't going to be impacted, if there's no route of exposure, we can grant a no further action. And examples are commonplace, these no further actions. I mean, gas stations throughout the world are now closed all the time with regulatory closure, even though they have benzene on them and PAHs, which are known carcinogens and toxins. I mean, these things are known carcinogens. There's still some debate about the toxicity of PFAS, but we're allowing benzene and PAHs to be left on gas stations because we can show there's no route of exposure. Now, some people argue, well, that benzene is going to biodegrade over time. Well, chromium plumes don't biodegrade over time, and yet all throughout the U.S. and overseas, sites are being closed or allowed no further action after we've retreated these chrome plumes from hex to tri. Now, if conditions change in the aquifer, if there's an EH or pH shift, there's a potential for hexavalent chrome to be formed again. But we trust, because we monitor once a year that water down gradient, that people are safe because that trivalent chrome isn't converting and it's not mobile. So no further action is granted. And we can say the same with PCBs and treated with activated carbon. So how does this relate to PFAS? Well, environmental risk, in this case, is equal to PFAS times exposure. Well, with injection of colloidal activated carbon into the subsurface, you've bound up that PFAS. You've bound it up onto the aquifer matrix itself. And once it's bound on the aquifer matrix itself, there's no route of exposure. It's sorbed out, it's down gradient, there's no potential for exposure because it's retarded. And when there's no exposure and no pathway for exposure, there's no environmental risk. So colloidal activated carbon can be used to eliminate the risk from PFAS. Strategies are simply cutting off a plume next to a surface water body. This is a no-brainer. I mean, trying to pump and treat next to a surface water body, it's generally a fool's errand. So to put in a barrier, this would be the plume stop here, along the edge of the surface water body, and simply covering over or excavating out the source, over time what you'll have is the plume will migrate into the plume stop, it will be sorbed there, and you will eliminate the route of exposure to that surface water body. You can also cut the time to a fraction of the time it takes for that by having multiple areas of plume stop. You'll see that that's much faster to treat the entire plume. If you have a potential source zone, you can actually contain that prophylactically with plume stop. And over time, you'll see that the contaminant will just sorb outward into the, or just move outward and sorb onto the plume stop. And a very interesting idea is to surround a production well or a domestic supply well with plume stop, and that way you don't have to treat it above ground. The contaminant will just go into the plume stop. So let's move into a case study. This is a case study of a furniture facility in Canada. And the background here, the initial drivers was hydrocarbons. We had hydrocarbons at 100 to 5,000 micrograms per liter, and the formation was a silty sand. We had a water table at 3 to 5 feet below grade. It was Rick McGregor was actually the person that actually applied this. And Rick is a very astute, technically trained. He was a Waterloo Masters trained hydrogeologist who runs a company out of Canada. And he was going to treat this hydrocarbon site with plume stop when he realized that there was a fire training area nearby. And he asked the question, I wonder if there's PFAS here. So there was sampling for PFAS conducted, and Rick McGregor at In-Situ actually found PFAS on the site. So this is a diagram here. In the upper part is the actual hydrocarbon plume area, and here is where he recognized that there was PFAS. The fire training area was right in here. And I want you to focus on these lower wells here, these blue dots. Here's the same blue dots down here, and you'll see here's the fire training area, and here's the PFOA plume, here's the PFAS plume, and here you'll see it. The red represents 3,400 nanograms per liter. So fairly high concentrations in this area. They took the plume stop that was actually planned for the petroleum hydrocarbon plume and spread it out across the entire area, including this PFAS area. The squares are actually the injection sites. The results, here's the actual PFAS and PFOA concentrations in the key monitoring wells before the colloidal activated carbon treatment with plume stop. And here's the highest concentration was the PFOA pre-injection at in this case, it's 30. I guess it's 400. Okay, and this is before treatment. After treatment, here's the final. You can't see it because it's too small. It's less than 20 nanograms per liter. So it's below detection for both PFOA and PFAS on all wells. I do want to mention that, well, the hydrocarbons all went to non-detect, the PFAS to non-detect. We're at 2 years of data and counting. There was a hit at 18 months of PFOS, and I believe that was at 20 nanograms per liter, and also PFUNA, which is the 11 carbon long perfluorinated compound, and they were just both above the level of quantitation but well below the standard. They're very suspect. Both of these compounds are very hydrophobic. They would be tightly bound to plume stop. If you were going to see something come off, it would be one of the hydrophilic species like the butanoic series, butanoic acid. So we were very suspect of that data, and it turned out that all data taken since then has shown that those compounds are below detection. So it's most likely a laboratory or sampling error. So at any rate, 2 years and counting, all non-detect. So another gentleman in Canada, unbeknownst to us, Dr. Grant Carey, he's an internationally recognized hydrogeologist and contaminant fate and transport expert. Independent of us, he got with Rick McGregor and studied the data. And on his own, he ran his models using the Freundlich constants that we had given him for plume stop, and he performed a sensitivity analysis, giving the estimate of longevity. How long will this barrier last? And here's what he showed. Here's again the area where the PFAS was treated in the monitoring wells. He took a point here, a well there, and calculated the breakthrough time. The time to contaminant breakthrough. When would you expect to see contaminants show up in that well? Based on the Freundlich isotherm that we gave him for plume stop, he estimated a longevity in excess of 100 years. you would not see PFAS show up at the level, regulatory level, for over 100 years. He then said, well, what if we're wrong? What if the KF is an order of magnitude lower than that, like 10 times? Let's say we're off by 10-fold. Well, then you'd only have an 80 to 90 year longevity. Let's say it's off by, again, twice as much, and let's say it's only 2,000 instead of 50,000. You'd still have 30 years of longevity of treating this site with what was injected. So again, plume stop is a very, very effective answer. So we then, just to give you an idea of the cost comparison, the total cost of implementing this was $73,000 to design. The product and the application was $73,000. This is not including any monitoring that the regulatory agency requires. Let's say that it didn't last 30 years. Let's say we're wrong, it only lasted 20 years. $73,000 is lasting 20 years. If you were to put in a pump and treat system and you use the most efficient GAC, granular activated carbon, it would take at least $150,000 to implement CapEx. And if we're doing 20-year comparison, let's say it only costs $60,000 a year, which by anyone's measure is low. By anyone that's skilled in the field, that's a low comparison. In today's dollars, that's $1.3 million versus 73,000. So there's really no comparison. It's much, much, much more cost effective to treat in situ with plume stop. This case was actually published in the journal Remediation, volume 28, number 2. It was last month it was published. So you're welcome to grab that. If you want to, I think that's available from us on our website. You can contact us on our website and download that. So in summary, colloidal activated carbon is a proven technology. It's been used on over 200 sites around the world. It eliminates the risk of PFAS in groundwater. There's no doubt about it. The site has been injected. It's now been proven. Experts have run sensitivity analyses, etc. It's a passive plume management approach. You know, if you ran the sustainability calculations on the carbon footprint of pump and treat versus colloidal activated carbon, you would be amazed at how efficient it is and how much more of a cost savings there is in terms of carbon footprint to the environment. It's very cost effective, low CapEx up front, and very low operating expense. And one last slide here to give you an idea of what's going on in 2018. In July, a major US EPA Superfund site was injected full scale with a plume stop. The project manager just told us last week that it's saving them hundreds of thousands of dollars a year in operating cost over pump and treat. Petroleum company in Saudi Arabia has a PFAS plume that's being injected. I believe it's this week or next week. I know that the shipments was on its way, so it'll be going, if not last week, this week. There's a large industrial project site in Western Michigan that the consulting group is working with us on, and they plan to go into the ground to protect surface water bodies from foaming PFAS in October. There's a national interest site in Italy. It's like their Superfund site. That'll be going in Q3. There's a US military base in Germany where plume stop is specified full scale to protect a domestic residence area down gradient of a fire training pit and airfield. And there are several demonstration projects, smaller demonstration projects that will be going on in Q3 and Q4, including a DoD facility in Michigan. So we're moving forward on many PFAS sites, and just in terms of plume stop in general, there's over 450 projects that are in the queue in the next year and a half to be injected. So it's moving forward at a fast pace, and it's a true solution for PFAS. So with that, I want to thank everybody for attending. It was very great of you to give us an hour of your time. And if you have any questions, I think we can turn it over to Dane to take questions. Over to you, Dane.
All right, thank you, Scott. That concludes the formal section of our presentation, and at this point we'd like to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you'll receive a follow-up email with a brief survey. We do appreciate your feedback, so please take a minute to let us know how we did. You'll also receive a link to the webinar recording as soon as it is available. All right, so let's circle back to the questions. We have a lot of questions today. First question is, this person says, a concern in my state, and that is Michigan, is that once plume stop is applied, it may need to be monitored for many years. The concern is that after a few years, there may be contaminant breakthrough, which makes it hard for no further action reports to rely on plume stop indefinitely. Can you speak to whether contaminant breakthroughs are an unfounded fear and why?
Okay, well, really good question. It goes back to what I was showing you from Dr. Grant Carey's work. We've done the sensitivity analyses on the length of time we expect to have the retardation, and it's on the order of decades and decades. I do think, though, that if we're going to do a no further action, that I think it should be contingent upon there being an annual groundwater sample taken from a sentinel well down gradient, just to assure that the public, in fact, is protected and that there is, in fact, a break in the pathway to exposure. So I think all the data shows that we should have decades and decades of retardation, but I think that there probably should be a requirement for a monitoring well down gradient periodically sampled. And if indeed it does show up that there is contaminant breaking through, let's say in 20 years, you can simply just put in another, in this case, $73,000 of plume stop, and you get another 20 years. We've done a lot of testing in the laboratory and shown that you can load plume stop on plume stop, and there's no impact on the amount of effectiveness of plume stop. Once you layer on another layer, you have another 20 years or 50 years or 100 years. So hope I answered that.
Okay, great. Thank you, Scott. Here's another question. This person says, I actually have a 10 ppm plume of PFOA and need to get it down to 10 ppt. Will plume stop work for that?
Yikes, 10 ppm, holy smokes. Okay, so that's a high concentration. I think that we'd be happy to look at that and see what type of impact we think we could have on it. We just would run it through the competitive sorption model and show you how much longevity we think we would have. I will say, though, that one of the places that's a limitation for the effectiveness of plume stop would be if it's in a fire training area where these high concentrations of PFAS might be commingled with diesel fuel that they were burning. When they go in light diesel fuel, they often put it out with the foam. If you have diesel fuel mixed with your PFOA, the diesel fuel unfortunately will competitively sorb onto the carbon and bump the PFOA off. So we'd have to look at that, and we just run it through the competitive models and do some testing on it. But we'd love to do that, in fact. So please contact us.
Okay, great. Probably have time for one more question. This question is, how, given the fact that the contaminant is not degraded and only bound up onto the plume stop in the subsurface, how has this been received by regulators?
Extremely well. I mean, regulators are aware that no further action is given in all the types of settings that I've mentioned. And if we can show that we bind it up, and if there's an adequate monitoring down gradient, there's no reason that this shouldn't be applied. If you look at pump and treat systems, when you put in a pump and treat system down gradient, remember you're drawing higher concentrations of these contaminants from up gradient down gradient. And as you're doing that, you're filling the flux zones with high concentrations, relatively high concentrations of these contaminants, which are forward diffusing into the lower permeable zones. Well, over time, though, that's going to have to come back out and back diffuse. So if you start pumping and treating as a solution, you're actually going to be retracting the entire problem if you're pumping down gradient. So, and if you're collecting the PFO or PFAS on activated carbon or IX brines, what are you going to do with those? Are you going to go take them off to another place and dispose of them? There's risk anytime you transport this stuff or dispose of it someplace else. So, I think a lot of regulators are now saying, why not just lock it up and do a reasonable job of monitoring down gradient to make sure that in fact it's captured and that there's no exposure to the public.
All right, thanks very much, Scott. We are out of time, so that's going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you need immediate assistance with a remediation solution from REGENESIS, please visit regenesis.com to find your local technical representative, and they will be happy to speak with you. Thanks again to our presenter, Scott Wilson, and thanks to everyone who could join us. Have a great day.